Okay, we will be solving some review questions from chapter 8. Let's start if you like. Okay, sample final solutions we have are chapter 7, section 1, and the question is question is as follows: determine whether the function is 1 to 1, y is equal to negative 2 over x. Is the function 1 to 1? The graph is given. Look at this. This is a butterfly graph, right, if you remember. And the function, we have to use which one? A vertical line test or horizontal line test, right? Horizontal line test is the key. We are going to apply the horizontal test to determine whether this is 1 to 1 or not. The answer is, of course, yes. And if you apply the horizontal line test, here's the answer actually. It is 1 to 1. Graph passes the horizontal line test. You just draw the horizontal line here, and the horizontal line intersects the graph exactly at one point. Therefore, this is a 1-to-1 function. Let's get the next question. Next question, this is chapter 7, section 2. Find the derivative of y with respect to x, question 11 in section 2. This is the function that's given, and the answer is negative 7 over x. And how do we find it? Actually, there's I think a variation of this question. This is a same type of question, but not the same one. So y is ln 3 over x, and first of all you write this in power form, the inside one, and you remember the derivative of ln x. It is 1 over the inside function times the derivative of the inside function. So 1 over the, okay, as I said, this is the derivative, the derivative of ln f of x is the derivative of 1 over f of x times the derivative of f. So 1 over f of x is 1 over 3x to the negative 1, and the derivative of the inside function is negative 3x to the negative 2. We apply the power rule to get that. And then we simplify. 3's are going to cancel. We have negative 1 left and 1 over x. That's the answer in this case. And I want you to try this on your own and try to get the answer is negative 7 over x if you could. Okay, next question. Question 40 in section 2, chapter 7. Evaluate the integral. It is this integral. How would you integrate? Okay, we are going to solve a variation of that question. Okay, this is the variation of this question. The limits are different. The function is just a little bit different. And the way we do, we know that you can take the 3. Actually, you can use substitution here. You can let u to be 3x minus 2, and du is equal to 3 dx, and 3 dx is du over u, and du over u, the antiderivative is 1 over u, the antiderivative is natural log of absolute value of u, and substitute u back, which is 3x minus 2, natural log of absolute value of 3x minus 2, and we are going to integrate from negative 1 to 0. Okay, because everything is in x, not in u. Okay, and then we put a 0 here. We get a natural log of absolute value of negative 2. Absolute value of negative 2 is 2. Minus, we put negative 1 here. You get negative 5 inside. The absolute value is 5. Minus ln 5. And if you combine it, natural log of 2 over 5 is the answer. Let's move to the other question. Okay, you can similarly evaluate this integral on your own and see whether you get this answer. Okay, check it out. Alright, there's another question. This is section 3, question 51. Evaluate the following integral. this integral we have the limit boundaries here, a to b, these values, 5e to the v cosine e to the v dv, and we can use substitution here. And let's see how we are going to do that. There's a similar one here, 2ev cosine ev dv, very similar. The boundaries are different, as you would see. This is another version of this question. We use the substitution first. We let e to the v as u, du is e to the v dv. We have e to the v dv, we let it to be u, and we have cosine u, and we take the 2 out. And then we change the boundaries as well. Okay, we change the boundaries as follows. Alright, and how do we do that? Here, if u is e to the v, then v is natural log of u. Okay, when u is this, what is v? V is ln. There's a, I think, typo here. Let me see. Let me fix that. Okay, until here we took the derivative and that's it. Okay, but the boundaries is, okay, v is equal to ln u. There's an ln pi over 6. There's a mistake here. Pardon, no, I'm so sorry. Whenever v is, this is v, not u. Whenever v is ln pi over 6, e to the ln pi over 6 is gonna give us, right? We put u is gonna be, there's the typo is the typo is u is equal, and there's no typo, I'm so sorry. U is pi over 6. Whenever v is this, u is gonna be pi over 6. Whenever v is ln pi over 2, we put it in here. E to the ln pi over 2 is of course pi over 2. We got these boundaries now. And then antiderivative of cosine is sine u, and we evaluate from pi over 6 to pi over 2. It is 2 times sine pi over 2 minus sine pi over 6, 2 outside. Okay, we factor it out. Sine pi over 2 is 1, sine pi over 6 is 1 over 2. This minus this is 1 over 2, and we get 1 as the answer. Now I want you to try it out with this example, do it on your own, and check whether you can get this answer as this answer, okay? If you do this substitution and then evaluate it like that, okay? Alright, so let's move on. Okay, next question is about L'Hopital's rule. This is chapter 7, section 5, question 6. Use L'Hopital's rule to evaluate this limit, then determine the limit using excuse me, let me turn this off. Okay, and then determine the limit using limit laws and commonly known limits. Okay, alright, so yeah, okay, first of all, what do we do? So it says use L'Hopital's rule to rewrite the given limit so that it's not an indeterminate form. As x approaches to infinity, we have infinity over infinity, okay? Then we can apply L'Hopital's rule. If we apply the L'Hopital's rule, okay, what is this gonna be? The derivative of the top. Okay, the derivative of the top is 12x plus 7. 12x plus 7, do we have it anywhere here? Actually, they do it very quickly. Alright, so if this is 12x plus 7 on top, and here 6x squared. Okay, if you take the derivative, 6x squared plus 3 down here, and then you're gonna factor out x, okay? There's a typo in here, I think, because 6x squared down here, it should be 6x squared. 6x squared. Okay, here actually you should try this on your own, and I'm gonna solve the solution because I don't want to write it on whiteboard right now. Instead, here's another question that's similar. The degree of the top is less than the degree of the bottom here, and if I set up my whiteboard, I can do the down one as well. This is infinity over infinity. L'Hopital's rule can be applied, and the derivative of top is 4x plus 3. The derivative of the bottom is 3x squared plus 1. And plug in infinity here. This is infinity over infinity. Apply one more time L'Hopital's rule. Okay, if you apply one more time, all right, right, then you have 4 on top and 6x here, and of course as x goes to infinity, this is 1 over infinity 0. Okay, this is another way to solve it. You're gonna take the highest degree here, x, factor it out. I mean, x cubed has the highest degree is x cubed, so factor that out. You have 1 here, 1 over x squared left, and 1 over x cubed down here. And if you divide this by x cubed, you get 2 over x and 3 over x squared. The bottom one goes to 1 as x goes to infinity, because this goes to 0, this goes to 0, and this is 1, and the top part goes to 0. Actually, in here, these solutions is given without the limits, L'Hopital's rule. What's the highest degree is x cubed, factor that out. This is not right, because you have to factor out x cubed. Okay, this is not right. This looks like right, because if you factor out x cubed, you get 2 left, and 3 over x squared left, and 5 over x cubed left. And if you factor out x cubed, you have 6 over x left plus 7 over x squared. This is going to go to 0, this is going to go to 0. We have 2 in the denominator, and this is going to go to 0, this is going to go to 0, and the answer is 0. So the solution here, D. And, alright, and if you do the L'Hopital's rule, it is, I think you get 12 over 12x. You should try it out. Okay, and of course this is going to go to 0 if you do it. And the answer to the second question is D, as we said, and the limit is 0. That's the end of the solution. Okay. Alright, this is chapter 7, section 6, question 3. Use a reference triangle to find the given angle. This is arc sine 1 over 2. We should ask ourselves for which angle sine of that angle is 1 over 2. And the answer is 30 degrees, right? Sine 30 degrees is 1 over 2. And you can take the reference angle like that. There's another question here actually, but just skip that because the question is not given here. Just forget that. Okay, chapter 7, section 6, question 80. Okay, here's a question. Use the method of completing the square along with a trigonometric substitution if needed to evaluate the integral. Here's the integral. First thing we do is we complete the bottom part to let me do a similar question, okay? Then you can do this on your own. Otherwise, it's like a story. Okay, here's the similar question, like t minus 2 over t squared minus 6t plus 10. First thing, we complete the denominator to a square, t minus 3 to the second power plus 1. And then we are going to let w is equal to t minus 2. And then w plus 3 is going to be t. Then dw is equal to dt. Alright? Then we write everything in terms of w. Instead of t, I'm going to write w plus 3 minus 2, which is w plus 1 on top. And here, w squared plus 1. And this is, everything is in w. Then what I'm going to do, I'm going to separate the numerator as follows. W over w squared plus 1 plus 1 over w squared plus 1. Okay? Alright, this one is arctangent, we know. And this one you can do by substitution. Let's do that first. Integral w over w squared plus 1 dw. And we use the substitution u is equal to w squared plus 1. Du is equal to 2w dw. And this is u. W dw is 1 over 2 du. And we get this in terms of u. We started in t. And we converted to w, and then we converted to u, so that we have the simplest form of it. And the antiderivative of this is going to be, let me see, the antiderivative of that is going to be ln u, right? if you integrate that ln u, then you can put back in w squared plus 1. So this part, the integral is here 1 over 2 ln w squared plus 1, and the integral of this one is going to be arctangent w plus a c, because this is an indefinite integral. And then convert everything to t now. W was t minus 3, and then put back in t minus 3 here, arctangent t minus 3 plus c, and then you can just, if you like, expanded it, or just leave it like that, no problem. That's the final answer. Okay, you can solve. So this is how you would do these type of questions, and you can use that method to solve this, and please do it at home and check it out if the answer matches with your answer, okay? As a practice. Alright, my next question, let's see what's that. My next question, okay, section 7, chapter 7, section 8, question 4. Which of the following functions grow faster than x squared as x goes to infinity? Which grow at the same rate as x squared? Which grow slower than x squared? Okay, that's the question. First of all, this is going to grow the same rate as x squared, because the highest degree here is x squared. So this is gonna be the same. Like this one is gonna grow at the same rate, and this one, this is not gonna go in the same rate actually. Let me see. Excuse me about that. Okay, this is gonna go faster. This is gonna grow faster because the degree is big, right? As x goes to infinity, and this is 11 to the x in the denominator. As x goes to infinity, 1 over 11 is less than 0, right? If a number is less than 0, and consider like 0.5 to the x, okay? X is getting bigger, so the bottom, so this is gonna go to gets close to 0 quicker, right? So, so these ones, let's yeah, okay, let's look at the solutions here. The function e and g grow faster than x. Let's look at e and g. Okay, this is gonna grow really fast because the base is bigger than 1. Definitely this is gonna go fast, and we said that e is definitely, so e and g is the right one, grow faster. So either a or c is the answer. Okay, then the functions a, b, and h grow at the same rate as x squared. Let's look at that. A, b, as we said, and h, that's right, these are grow at the same rate because the highest degree is x squared, and the highest, yeah, that's true. And the functions c, d, and f, let's look at c, d, and f grow slower than x squared as x goes to infinity. C, d, f logarithm is gonna definitely be slower, and if you divide this by x squared, you get 1 over e to the negative 2x. So this is a function that is less than 1. All right. So in order to grow at the same rate, they have to be, if you take the ratio, the limit goes to 1. Okay, that's the idea. That's how you would do that. Okay, and this is less than that, so grow slower than x squared, and logarithm is going to be always like that. So the answer is going to be A. Okay, that's the end of chapter 7. Let me see whether I can, whether you could do, yeah, this is actually, you don't know which functions they are comparing, but here's how you should look at it. Okay, this is an alternative question. So you are comparing x squared plus square root of x with x squared. You just take the ratio and let x goes to infinity and see whether the limit is 1. Yes, the limit is 1. You look at the limit, so they grow at the same rate. So look at the ratio of the two functions. If the limit is a number that's bigger than 1, then they are gonna grow with the same rate. Take the ratio of x squared e to the negative x and x squared, you get 1 over e to the x, which is 0. Whenever this is less than 1, the top one is slower than the bottom one, okay? And then we are comparing this function with this function. We take the ratio and we can write log as ln x squared over ln 10. Ln x squared is as x goes to infinity, this goes to infinity, this goes to infinity. We can apply L'Hopital's rule to find the limit. If you take the derivative of that, okay, actually first they don't take the derivative, they just simplify it. This is like 2 ln x, and then they take the derivative. The derivative of ln x is, they apply the L'Hopital's rule here because it's infinity over infinity still. And this is 1 over x, the derivative is 2x. What we get 1 over 2x squared. And as x goes to infinity, this is going to go to definitely 0. So therefore, log function is going to grow slower than x squared. Let's compare this, and this. See, the degree of this is bigger than this. So if you take the ratio, the limit is going to go to infinity. So it is bigger than 1. So therefore, the top one is faster, grow faster than x squared. Let's get 1 over 10 to the x and x squared. Again, we take the ratio, look at the limit. Okay, this is exponential, but I'm going to rearrange it, and I'm going to write 1 over 10 to the x over x squared. Look, as x goes to infinity, this goes to infinity, this goes to infinity, so this goes to 0. So this top part is going to, actually, the top function is going to grow slower than x squared because the limit is 0. Let's get 1.1x over x squared. Okay, so you can write as x goes to infinity, this is going to go to infinity over infinity. Let's apply what? L'Hopital's rule. L'Hopital's rule says ln 1 times 1.1 to the x over the derivative of x squared is 2x. And top part goes to infinity, bottom part goes to infinity. Apply L'Hopital's rule one more time. ln 0.11 squared we get, and 1.1x, and the denominator has the derivative too. As x goes to infinity, this goes to infinity. This is going to tell us that the limit is bigger than 1. So that says this grows faster than x squared, okay? And let's compare x squared plus 100x with x squared. They have the same degree, so they grow with the same rate. The proof of it is just you take the limit of the ratio, and you're going to see that the limit is 1. Okay, that's how you should handle. You have to show that the limits are the same. The limit of the ratios is either bigger than 1, less than 1, or equal to 1. Okay, that's the end of chapter 7 solutions.